Hello, everybody. Welcome to Earth Science. Let's talk igneous rocks. Before we start the notes, what I'd like to do is jump over to the reference tables. Pages 6 and 7 contain most of the rock stuff. We did do minerals, remember, on the very back cover of the reference tables way back here. But for the most part, rocks and minerals, what we need are on pages 6 and 7. And that guy that we've already studied is randomly stuck in there too. The rest all has to do with rocks. Where I'd like to look, before we get going, on the three, we're going to do like notes lab, notes lab, notes lab, right? And they're going to be the order is igneous, then sedimentary, then metamorphic. But to keep a context on where we're going, let's make sure that we always look back to the rock cycle to see how these rocks are formed. If you go and become a, like professor level geologist, you would really get into like probably just one aspect of one of these. We're just going to generally study all of them in a very light way, right? But friends in SUNY Oswego, there's a specialist in sedimentary, there's a specialist in igneous, and there's a specialist in metamorphic, and they kind of like interplay with each other, like like fight about why their rocks are the coolest of the rocks, right? Um, so why would the igneous ones be? I guess like the only thing I can never say is volcanoes, right? They come from rock that was part of Earth's interior that was melted, rock that got hot enough to melt, which is an impressive amount of heat, and then they solidified from there. And so the ones that we can witness the most easily forming are out of volcanoes, right? But there's also other types, and that's what we're going to get into today. Is not just igneous, but what within igneous are the different types of rocks that all are part of that category. Keep in mind though, this rock cycle very easy to use. You have to go forward on arrows is really the only rule. Think of it like a roll and move board game. Can't go backward on arrows, only forward. So how do you get to igneous? The only paths that get there are if one of the other three types of rock melts. Melting, melting, melting. That produces magma, melted rock, and then that magma cools and goes through solidification. That will form an igneous rock. And we'll look at various ways in which that happens to identify all these different igneous rocks. If your first look at this reference table is right now, you're probably saying, holy cow, it's intimidating. And it is. There's a lot going on here. But if we unwrap this just right, and if you stick with me on this video, which is going to run a tiny bit long, but you'll stick with me, do it, please. Um, we'll figure out how to unravel this thing and make sense out of it. It looks like a mess right now. In about 20 minutes, you're going to be in great shape. Okay? So over to your notes. This is what you should be looking at. So let's just broadly step back again and say, okay, what are igneous rocks? And here's that word from the rock cycle again. Rocks that form from the solidification. I'll make that a little bigger and more colorful. A little bigger, yeah. Solidification of magma or lava, and what that requires is cooling. Cooling of magma or lava. Excuse me. Magma is the term for it when it is inside the earth. Lava is the term for it when it is on Earth's surface. So this would be inside Earth. This would be on Earth, essentially. So nobody's ever seen magma. You can only see lava because that's when it's on the surface here. Either way, take that hot melted rock and cool it off so that it resolidifies, which is a phase change. I mean, it's you're used to say turning water into ice, right? You take a liquid, you decrease its temperature till you get to the freezing points, then it solidifies and it turns into an ice cube. This is the same principle. Take a liquid that's at a higher temperature, cool it down past its freezing points, and it turns into a rock. All right. So to be able to identify igneous rocks, when it's your turn for the lab, and you get your little box of rocks like we're getting used to here, you open it up, you got a whole bunch in there. These are the two things you look for. So this is like, I did little like boxes with check marks on the other one. I should have done it here too. But if you can look for these two things, then the job's easy. And they're going to look intimidating at first, but again, stick with me. You're going to get there. We have to learn to observe a rock's composition, which means what is it made out of? Believe it or not, you're going to be very good very soon at picking up an igneous rock, looking at it, and knowing what it's made out of. And its cooling history, which means how quickly did it cool off? that has a big effect on what the rock actually looks like. Did it cool very rapidly or did it cool very slowly? So the way we'll tackle these here in this note sheet is the composition we'll talk about right here. What's the rock made out of? Cooling history. We'll come back in a minute and talk about right there. All right. I like to start with composition. So here's some new vocab words. I mean, there's more vocab words up here. And again, is this intimidating? You got to have all these words down. Extrusive, intrusive, felsic, intermediate, mafic compositions. It looks like a lot, right? But don't worry. I'm going to show you tricks. You're going to succeed. So your job will be, when it's time to pick up the rocks here, tell me, is the rock felsic, intermediate, or mafic? And how do you do it? Write with me if you would, please. The felsics have light color. The mafics have a dark color. I'll come back to intermediates in a minute. I'd like to say, as kind of a highlight right here, and I'm going to show you where this lives on the reference table, especially if you see pink. If you see pink, it's no doubt felsic. That makes your life easy. Okay. Let's also say over here, the mafics are more dense. They're going to feel heavier, whereas the felsics are less dense. They're going to feel lighter. Now, you're not actually going to calculate density like we did at the beginning of the year, but if you kind of just feel a felsic versus a mafic, you're going to notice that these guys are more dense. And the reason for that is what these are made out of. These are made out of two different elements. I wouldn't say totally made out of, but heavy in. You will predominantly find Fe and Mg in these rocks. A lot of that stuff. That's iron and magnesium. Should you ever need it, should it ever pop up, do remember we don't have a periodic table in this reference table, but we do have the ones that are common in earth science listed right at the very bottom of the last page with the minerals. Fe is iron, Mg is magnesium. So expect more of that in mafic rocks. And again, believe it or not, you're going to be able to tell that right away just by looking at it. The less dense ones contain silicon and aluminum, Si and Al. Okay. What about these intermediates? Well, what I would expect, these are more light, these are more dark. These are going to be more of kind of a gray, like an in between. What can also happen, what definitely will happen with one of them, is you'll see like a 50-50 mix of black. Let me just do another space here, of black and white. So if you can't quite say this belongs on the dark side or on the light side, it goes in the middle, because this is kind of a continuum. Magmas are mixes of all these different things, right? So if the elements in that mix are more towards this side, it's lighter in color, it's more felsic. More towards that side, darker in color, more mafic. But it can really be anywhere on that continuum. Okay? So bad news and good news. The bad news is you got to know this to get through this lab and get through the tests and get through these questions on the regions. There's no way you're going to make it without knowing this stuff. And if it looks like, oh man, that's a lot, don't worry, because what we're going to do, pop over real quick to the reference table that's on the bottom of the page right over here. And you will see. Please circle with me. And if you were in class, I'd be asking questions. I'd say, circle right here, where it says that these rocks are felsic in composition. And I would say, you, Steve, tell me about the density of felsic rocks, which we just wrote up here. Yes, I know. Maybe you remember that it's less dense, but you don't have to memorize it. It's right there. It's a lower density. Its color is lighter. Come over here with me to the other side. This side of the continuum is the mafic, which has the Fe and the Mg. It is higher in density and it is darker in color. So really, when you get this lab's easier than minerals. You should have already done minerals. That one's a little trickier, and there's more going on. This one, just put the lights on this side, put the darks on this side. You're halfway there. Put the intermediates in the middle. In fact, let's do this right here. This column right here in the middle, draw a little arrow with an eye. That's where intermediates live. So this side is felsic. This column in the middle is intermediate, and really these are mafics. I'm not going to give you either one of those two in the lab. Like, they might be in questions or science, regions questions might bring those up, so I wouldn't totally cross them out. But I promise to not have those in the lab. So basically, these are the felsics, these are the intermediates, these are the mafics that you will deal with. And that's it. That's half the battle in the lab. Light colors, dark colors, middle colors. And just by looking at that, you have gone sorry about that. Just by looking at that, you've gone and identified the composition of the rocks. You've seen the elements inside the rocks just by dealing with the color and the density, if you want to think about it that way. Hey, you've already done the mineral lab. If you hopefully you recognize some of these names from that mineral lab. I'd like you to right now, just for sake of it, circle pink right here because again, seeing a little bit of pink, seeing a little bit of potassium feldspar. Let me grab my potassium feldspar from the mineral lab if I can pause. Yeah, if you remember this one from the mineral lab, kind of chunky, pinkish potassium feldspar. What we're saying with all these now, these are the minerals. These were isolated mineral samples. Now we're saying here's a rock that's composed of a whole bunch of these. So on the felsic end of the spectrum, you're going to expect to see some of those pink potassium feldspars and quartz and plagioclase feldspar and biotite and ineffable. Intermediates, you expect to see these minerals. Mafics, you expect to see these minerals. I don't expect anybody's going to memorize exactly what all those minerals look like from that lab, but if we start to play with this enough, you're going to see enough combinations where you can really whittle down what's going on and answer questions like a pro. And again, the pink, which is why I wrote it up here, like is really a giveaway for putting yourself over towards the felsic end. There's going to be rocks where you're going to say, I don't know, is this light colored or is this in the middle? If you see pink, boom, felsic. Easy peasy. All right. Good. So listen, that gives, again, that's half the lab. That's going to say, are we over towards this side or are we over towards this side? Now what we got to do is say, how do we know where it is like top to bottom? How do we know the difference between these ones and these ones? And what that comes down to is figuring out the cooling history. And again, believe it or not, just by picking up a rock and looking at it, you're going to be able to tell me how quickly that rock cooled off. So we have two basic categories: extrusive rocks versus intrusive rocks. Intrusive inside the earth, extrusive explodes out onto the earth. So down here, deeper within the earth, we've got our magma, right? Outside of that, we have rock that's already formed, like Earth's cool crust. And in places for different tectonic reasons that we'll discuss in Market Period 4, magma comes squirting its way towards the surface. Not randomly, it doesn't happen in Pulaski, but in places where the tectonic situation is right, this happens. And magma will melt its way and create these like pipelines and occasionally come popping right out the surface where it explodes under the surface in a volcano. Other times, it works its way towards the surface, but doesn't quite get all the way there. Remains deeper within the earth. More shallow than it is permanently hot with the magma, but not all the way to the surface. So both are going to cool down, but the giant difference is the speed at which they cool down. These guys inside the earth cool slowly. They're like insulated. It's like using the earth as a giant thermos that traps the heat. It doesn't let it escape as quickly. And though they're far enough away from the magma that they are going to cool, they're going to do so very slowly, like over years and years and years and years, if not longer. Versus extrusive rocks that explode under Earth's surface, it's cold up here. Even if it's a hot day in a hot part of the Earth, if you're magma, it's cold. So these come out and have no choice but to cool quickly. Your job is to figure it out by looking at the rock whether that happened. And if that sounds scary, don't worry, it's not bad. What you're going to look for is what do the minerals look like? Okay, let me grab this rock right here. When you look at a rock and you look at the individual greens that make up that igneous rock, can you see them or not? If you can see them, this one right here, this is a pegmatite, must have cooled ridiculously slowly. These are huge crystals. I don't know how great they're showing up on camera, but if you can see that these are like big, huge bits. There's a feldspar. I can't point backwards here. Right there. I mean, it's as big as the end of my finger, which is huge. For them to form, for them to get that big, it takes time. Out of a liquid magma that has all of these elements banging around in it, as it starts to cool and solidify, each atom has to find another atom that is its counterpart that will make up those minerals. Where is it? Potassium feldspar. All of those things have to form exactly like that. You need a potassium, an aluminum, three silicas, and eight oxygens to all link up just right to form that. It takes time for that to happen. And the more slowly it cools, the larger the crystals can get. So what we're going to say here, this is a new term for large crystals. We're going to say it has a coarse texture. And what that means is large crystals, which form over a long time because it cools so slowly. Versus things that come out, they just have to form. How are you going to have all those things find each other in a matter of minutes? You can stand in Hawaii and watch rock go from lava to solid rock in a matter of minutes. You're not going to have a time to form a big crystal atom by atom over the course of minutes. It just forms. So what you end up here with is a variety of possible textures. If it cools reasonably slowly, like a Hawaii situation where it's out, it's flowing, what you'll get is I should change colors, fine texture, which means it has small crystals. Bordering on you can't even see them; they're so small. Maybe it may be just barely visible. Versus these will be visible; you can see them. Sometimes because it like maybe it goes right into an ocean, or maybe it's right where it popped and it blasts into the air, and that cools it like very quickly. I know this is kind of silly to say, but you can either cool quickly or you can cool like really quickly. So if we cool very quickly, what you can get are two other textures. Glassy. A lot of people have seen the volcanic glasses like obsidian, just looks like a hunk of glass. Or this is a new term. Again, don't panic. Vesicular. It means it has gas pockets, like Swiss cheese. So if it like again, if it hits the ocean water, which is even colder than the air, or if it like blasts into the air and cools quickly that way, you might end up with those. If it's just kind of flowing and going regular plain old fast, you might get fine. And again, if it cools very slowly, you'll get coarse. I'm gonna make that red just to for the heck of it. All right. So back to the reference tables. And this intimidating reference table, hopefully we're starting to make sense out of. And here's your job. Light color over here, dark color over here. Now what separates the like top from bottom? Well, all that stuff that you got to know is still sitting here. Intrusive rocks, we just said. Here's a new term for them. They can be called plutonic. Well, what do we say about them? Intrusive rocks cool slowly and have this coarse texture. So I guess one thing you got to kind of keep in your head is this whole intrusive does mean that it cools slowly. Otherwise, everything's on this table. Watch. Intrusive that cool slowly, we know, come way over here to where it lists texture, and it will tell you that the texture is either coarse or very coarse. They even give you the sizes. I can't recall a Regents question where they actually use the sizes, but they're there. Um, and non-vesicular, but that'll make sense when we see this one. All right, that's it. The rocks that form inside. So now, hey, your job tomorrow is going to be, or whenever you do this lab, light in color, come on over here. If it's a coarse texture, come on right here. That'll be granite. This one right here is a pegmatite because the crystals are so big. Dark in color, but big visible coarse crystals, it's a gabbro. I'm not going to have a diabase on there to keep our life simple. Okay. What about the others? Extrusive, meaning it cooled quickly, and depending on how quickly you got either fine, glassy, or vesicular. Here it all is. Extrusive. Another word for them are volcanic rocks. And again, the only thing that you got to keep in mind to make it here, because you can read the rest off the tables, is that this cools quickly. What does that do? Should I know that, Mr. F? Yeah, you should know it, but you can just steal it from the tables. If there are any of these extrusive rocks, come on over and see the texture. They're either going to be fine, vesicular, or glassy. And I know there's a couple of weird combinations here where you say that's a little bit of both. Okay, don't worry about it. You're going to figure it out. It's going to be fine. And it even tells us, in case you don't remember, what vesicular means. I mean, hey, what if there's a question that just asks about that? What's vesicular? Those are rocks that have gas pockets. Easy peasy. Okay. So we're done, really, right? I'm going to fill in this last little bit here, but light colored on the left, dark colored on the right, middle in the middle. Coarse on the bottom, glassy on the top, vesicular in the middle, fine right there. And it's just like line them up, and I'll give you a great big reference table again. You'll have a bunch of samples, and you'll just try to put them on the ones that are there. Okay. Let's do a couple practice things though. Let's actually do this first right here, and then we'll do a couple practice things and get you out of here. Thanks for sticking around this long. As a note, texture refers to the crystal size, the minerals in the rock. It's tempting to say that texture must mean what does it feel like. I don't blame you for making that mistake, but that's not how geologists see texture. If you took this rock, which I'm saying has a coarse texture, and when I say coarse texture, I'm referring to this. It's actually very coarse. I'm referring to this, that the crystal sizes are at least a centimeter or larger, right? I'm not talking about the idea that it feels kind of jagged. If I took this rock that feels kind of jagged, put it into a rock tumbler for a while, or onto like the lakeshore where I showed you all the abrasion with all those cobbles, so that it gets all round, it would feel smooth, but a geologist would still say it's a coarse texture because we don't care about how it feels. That's just how it's been treated since it left. If you have granite countertops at home, those have been polished and like coated. They feel very smooth, but if you've got bits in it, it's a coarse texture. That's what we talk about when we say coarse texture. Okay? We don't really care about how the rocks feel. That's just how the Wards company shipped them to me, right? Or how I found them out on the street somewhere. Vesicular. Again, it says it right there, so don't panic on it. You got it. A rock that contains gas pockets. Um, I always compare this to popping open a 2 liter of soda that's been shaken up a little bit. There's carbon dioxide in that liquid. If you shake it up a little bit, get it agitated, and then pop it, release the pressure instantly. That under that release of pressure wants to turn to a gas that makes all those bubbles in your soda and sometimes comes squirting out the top, right? That happens here in volcanoes too. Really the same exact thing. If we rapidly release the pressure by, say, blowing the top off of a mountain like Mount St. Helens, that means the CO2 that is under pressure, stuck in that liquid magma, um, suddenly can turn to a gas. Sorry, I got to do that a little squirrely. And when it does, just like the soda, it creates bubbles and then goes shooting out. And those bubbles, then, if that rock cools very quickly, get preserved in the rock. Vesicular, it's a silly way to say it, probably improper, but vesicular rocks are like frozen soda foam. If I could take soda foam and somehow like freeze it instantly, like liquid nitrogen or something, it'd be the same thing. I'd have a vesicular piece of soda rock. I don't know what that would be. But that's the idea. And you'll get it with the pumice. A lot of people have seen pumice before. It's so light it can actually float in water sometimes, and it's filled with little tiny gas pockets. Swiss cheese. And glassy. Sometimes a rock cools so quickly. Come on. That technically, mineral, like in the sense of a mineral crystal, they don't form by the true definition of a mineral. And you just get this glass. They've got no option. They've got to cool. They're not going to remain as a liquid, but they don't have the time to form what technically is a mineral. It's just kind of a mishmash uh, glass. Okay, this can mess with color. When over by my door next time you're here, there's a little tiny postcard that blows up obsidian like 100 times or something, and you can see that it's actually quite clear. But because of the jumble in here, this is like the one rule breaker in there. Obsidian usually appears black, even though it is composed of minerals that should be light, should they have time to form. So, not a big deal. You'll see it. And everybody gets obsidian. That's not going to be an issue. All right, here's where I leave you. I want you to complete this. What would these 6 rocks look like? These are the 6 really basic igneous rocks. For example, the first one, what would a felsic extrusive igneous rock look like? Well, it's felsic. It's light in color. I have that memorized because I'm crazy about this stuff. You could come down here and say, I don't remember, but oh yeah, felsics are lighter in color. It's extrusive. Again, I know that. What if you forgot? Extrusives generally have a fine texture. And if you said one of these other two, you wouldn't be wrong. You can only be wrong if you said coarse. So light color and fine texture. If you can figure out those other five, you're in good shape to start this lab. Okay? What is a felsic intrusive? What is a mafic extrusive? What is a mafic intrusive? And these two are kind of like the grayish color. Well done. Thanks. I know that was a little long, but 25 minutes. You stuck with me. Thanks, everybody. We'll catch you in the lab.